Hello everybody and welcome to ATC Maths and Science tuition. Today we'll be looking at cubic graphs and more specifically how to sketch a cubic graph. Now, in order for us to sketch a cubic graph, we need to know a few things. For instance, what is the standard equation? What is the basic shape of a cubic graph? And how to find those important points that we need to plot on a Cartesian plane. So, without any further ado, let's begin. So we're looking at cubic graphs, and our basic equation, or the standard equation of a cubic graph, is f of x is equal to ax cubed plus bx squared plus cx plus d. Now, as to the shape of a cubic graph, well, I like to describe it as the N shape or the reverse N shape. Now, which one of these two shapes we end up dealing with actually depends on the coefficient of x squared. So if x squared, the coefficient of x squared of x cubed, happens to be a positive number, we would get this N shape. But if the coefficient of x cubed happens to be a negative number, then we will get this reverse N shape. Now, with that being said, if we have to look at, on a Cartesian plane, just a random cubic graph being drawn in, you would notice that, well, there's certain important points on this cubic graph. It's 1, 2, 3 x-intercepts, the y-intercept, and 2 turning points. Now, if we happen to have these 6 points, once we plot them on a Cartesian plane, we'll be able to find anything that we're looking for, or we'll be able to draw this graph quite easily. So the question is, how would we actually find these 6 points? Let's begin with the most difficult of these 6 points that we require to find, which would be your 1, 2, 3 x-intercepts, right? Now, to determine x-intercepts, well, we find x-intercepts the same way we find it for literally every graph under the sun. We let y equal to 0 and solve for x through factorization, obviously. So if we're going to be dealing with factorization, we in grade 12 should know the typical ways of factorizing a quadratic, etc. The problem here is we're going to have to factorize a cubic function. Now, in order to factorize a cubic function, depending on your teacher in school, they would have probably discussed with you one of two methods: either remainder factor theorem and analysis, or remainder factor theorem leading into synthetic division. We will do both techniques at once. So, let's say, for instance, we have the equation f of x is equal to x cubed plus 5x squared plus 3x minus 9. And we want to find, let's say question A, find x-intercepts. So the first thing we would do is we'd say, okay, for this particular equation, let's set y equal to 0, right? And then we're going to work with it from there. Now, we need to first, before we even begin with that usual typical step in finding an x-intercept, we need to apply what is known as the remainder factor theorem. Now, what is the remainder factor theorem? So the remainder factor theorem, to put it in simple terms, we need to find a value for x, some value, x equal to a, some number, so that f of a will be equal to 0. So we need to just find some number a that when we substitute it into this equation for x, it will give us an answer of 0, the total being 0. Now, a could be any number, anything from negative infinity to a positive infinity, which seems a little bit crazy to choose from. Like, how do we know? I mean, that's an infinite number of numbers. Well, if we look at the constant here, this constant, d, minus 9 in this case, the value of a will always be a factor of this constant. So a will be either plus or minus 1, plus or minus 3, plus or minus 9, the factors of 9. Now, which one will it be? We could use trial and error. However, if you're in the South African schooling system, well, they like to use either plus or minus 1 as a factor. If you take a look at the past year papers, you'll see that it's a deliberate design that they like to use plus or minus 1 as one of the factors. But obviously, that's not a rule. That's just something that we notice when looking at the past year papers. We should remember as a rule that a is going to be a factor of the constant, plus or minus, obviously. And the only way for us to figure out exactly which one will fit this remainder factor theorem rule is through trial and error. So we want to start off with the whole plus or minus 1 bit, right? So let's try positive 1 to start, right? So this would mean f of 1 is equal to 1 cubed plus 5 times 1 squared plus 3 times 1 minus 9. Quick check in the calculator, 0. So this tells me that x minus 1 is a factor. Now, let's follow the way this blueprint would work, right? I'm not saying that let's switch the color to actually to blue. Now, when it comes to the next step, remember, we want to have the equation set equal to 0. And this is what we're going to have. X minus a into x squared plus bx plus c. That's going to be what our original question would factorize into. Now, we already, obviously when you're writing your solution, you're writing this, right? This is just the format of the answer that we're going to be following, right? So what we will see when we are doing our solution is this. We would write 0 is equal to x minus, and we just found out that a is 1. So x minus 1 into x squared plus bx. Now, here we need to figure out what this c is. So remember our original equation. I'll just write it alongside here on the side. It was x cubed plus 5x squared plus 3x minus 9, right? So we can see it. Now, if we think about it, whenever we factorize anything, when we multiply it out, we should get back to the original. So that means if I say 1 times c, it should give me the constant in the original, which is minus 9, which tells me that c must be plus 9, positive 9, because negative 1 times positive 9 will give me the negative 9 that I'm looking for when I multiply this out. So far so good. I've got everything except just this b, and once I get the value of b, then I'm good to go. Then I can say to myself, okay, what I'm going to do is I'm going to be able to factorize the second bracket, which is a trinomial, into 2 more brackets like how we normally factorize, and we've got our 3 factors, our 3 x-intercepts. Now the question is, how do we find this value of b? Well, let's just write this. We've got our statement here above. So this is how we would find b. So the method we're using now is the analysis technique, right? So we're just analyzing how to get the equation. We will also discuss how to deal with synthetic division a little later on. So what we have here is the following. We're going to take this number. So this is the steps to finding b. So we take our value of a and we multiply the x squared. Then we take the x and we multiply our bx. And we add them together. See the plus sign here. And we set it equal to the x squared term in original equation. So if we were doing that, this is what we would have. We would say minus x squared doing the first multiplication plus bx squared doing the second is equal to the x squared in the original. There's our original. That's our x squared in the original, which is 5x squared. Now, if we divide everything by x squared, all the x squareds cancel off, and we're left with minus 1 plus b is equal to 5. Taking the 1 across, b is equal to 5 plus 1, so b is equal to 6. Now that we have the value of b, our equation now stands as 0 is equal to x minus 1 into x squared plus 6x plus 9. This is a trinomial which can be factorized into, it's actually a perfect square trinomial. Normally we would expect two brackets here, but this being a perfect square trinomial will just become x plus 3 all squared, which is technically two brackets, right? So from here we can set each bracket equal to 0, so x is equal to 1 or x is equal to minus 3. So the first x-intercept is 1 and 0, and the second one is at minus 3 and 0. It's also very interesting to note when we try to sketch this graph, this bracket being squared. We'll just take special note of this, and then when we deal with the graph sketching, we'll be able to understand fully what was going on here. So now we've found the x-intercepts, which means if we go back to our graph, we've got 1, 2, 3 things, check. We just require these next major 2 points. Because the y-intercept, well, y-intercept's really easy to find. We'll discuss this first because, well, there isn't really much to discuss there. And then we're going to go on to the turning points and what we're supposed to do. So for the y-intercept, you could do it one of two ways. But we're just going to take the shortcut way after we discuss the usual way. So everybody knows, if you got to grade 12, y-intercept, let x equal to 0. Solve for I, right? The usual stories. However, in the cubic graph, the y-intercept is simply whatever d is the constant, right? So in the question we're working with, the y-intercept would be minus 0 and minus 9. So for us, 0, minus 9. So we've got our 1, 2, 3 points to plot. The only thing we need to discuss now is how to find the turning points. However, before we go on to how to find the turning points, let's just discuss one thing about the word turning points. Sometimes when you're looking at question papers, they won't refer to turning points as turning points. They refer to it as stationary points. So it's an alternate name for it. Or occasionally they'll like to call it local minimum or local maximum, depending on whether you're looking at, so if this is the cubic graph, the maximum or the minimum, right? So maximum, minimum. Now how would we go ahead and find the turning points? So the method is simple. It is find the derivative, set it equal to 0, solve for x. Once we have x, sub x into your f of x equation, and solve for y. And then you would have your x and y value for your turning point. Right? Now the question is, and this is actually an important question, because it's not nice to just follow steps blindly when we're trying to solve something. Why do we set f of x equal to 0, f prime of x equal to 0 when we're trying to find these stationary or turning points? It has to do with what the word derivative means. Derivative, we should understand, means gradient of curve. And so, if we look at the graph, at the turning point, the gradient, the slope of the graph, is 0. That's why we set it equal to 0. Too often you will see sometimes people say finding the derivative and setting it equal to 0 for no reason. We must know the reason why we're doing it. So, from here, let's take the same equation that we were working with, right? And let's find this derivative. Then set it equal to 0. So our original equation is f of x is equal to x cubed plus 5x squared plus 3x minus 9. So the derivative f prime of x will be equal to 3x squared plus 10x plus 3. We set this equal to 0. And now we factorize like we would normally do. So 3x, x, and so this should be plus 3 plus 1. From the first bracket, we would end up with x is equal to minus 1 over 3. From the second, x is equal to minus 3. Right? Then what we would do here is we would say f of minus 1 over 3 is equal to minus 1 over 3 cubed plus 5 into minus 1 over 3 squared plus 3 times 1 minus 1 over 3 minus 9. Calculator. We get our answer. Calculate that in a little bit. And so this would give us minus 9.48, which means the first turning point is minus 1.3 for x and minus 9.48 for the y coordinate. Then we need the second turning point, but we don't even really need to find it. This is one of those cases where the turning point is both the turning point and the x-intercept. You'll know that because the value's been repeated when you are finding the x-intercepts. Because when you're finding x-intercepts, you expect to have 3 distinctly different x-intercepts. But this time round, we actually ended up with just 2 distinct x-intercepts, which would mean that this should give us 0, right? So minus 3 and 0. Now all we need to do is plot all the points, the x-intercepts, the turning points, and the y-intercept on a Cartesian plane. So our first x-intercept was at 1 and 0, the second one at minus 3 and 0, and then minus 1 and minus 9, or minus 1 over 3 and minus 9.8, which we'll estimate somewhere around here. 9.48. Y-intercept at minus 9, and so we would join all these points to get our cubic